In section 4.1, we're going to be dealing with two topics, detour proofs and midpoints. I'll get to midpoints towards the end. That'll only take a couple of minutes to get through. But the main topic that I'd like to discuss is detours. Now, detour proofs are proofs in which we take one set of triangles, prove them congruent, use CPCTC, and prove a second set of triangles congruent. So basically we're taking a detour because we have to do one thing before we do the second. Now, a more detailed outline of how this works is given here. First, we're going to use any given information, definitions, theorems, etc., as we normally would in any other proof. We are then going to prove a set of triangles congruent. Remember, we have four methods: ASA, SAS, SSS, or the HL postulate. After we prove the triangles congruent, we are going to use CPCTC, possibly twice, usually once, and then we're going to look to see if we've been given any additional information. We can again use theorems, definitions, etc., and that will allow us to prove a second set of triangles is congruent. Afterwards, we may or may not use CPCTC. Again, we could also go beyond CPCTC. It just depends on what the problem is asking us to prove. I am going to walk you through an example problem. First, take a good 30 seconds to a minute here and take a look at the given information. Take a look at what we are trying to prove and think about a strategy that you would incorporate in this problem. Based on the given information, hopefully your first thought is we are going to try and prove triangle BCG congruent to triangle DCF based on the fact that we're given BC congruent to CD and CG congruent to FC. Some people might think, maybe I'll try to prove triangle ACG is congruent to triangle ECF. However, it's not possible because the line segment CB ends at B and doesn't continue on to A. If it was line segment CA congruent to line segment CE, it'd be a different story. Now, we have to think of some previous theorems, definitions, etc., and we're going to go with vertical angles. Angle 1 congruent to angle 2. Why vertical angles are congruent. Now, when I mark my diagram, it should be very obvious why we have congruent triangles. Triangle BCG is congruent to triangle DCF. Reason, side angle side. So now, that's our detour. We've proven triangles congruent. We have to use that to our advantage so that we can prove triangle ABG congruent to triangle EDF. Reason being, our proof statement is that AG is congruent to FE, not part of the triangles we just proved to be congruent. So actually, I'm going to use CPCTC a couple times here. First off, I'm going to say line segment BG is congruent to line segment FD. Reason, CPCTC. Now, I can use CPCTC as many times as I want. Well, that's not really true. 3 times max. Okay? But I'm not going to use it 3 times. I'm going to use it one more time, though. So the red line segments, that's how I use CPCTC the first time. But I also am going to show that angle 3 is congruent to angle 4 by CPCTC. And I kind of cheated because I looked at the given information a handful of times before I started the proof. And that's why I knew I needed to use those two pieces of information for CPCTC. Now, notice angle 3 and angle 4, they're not in the triangles we're trying to prove congruent. Okay? So we need to take another step. We're going to say angle ABG is congruent to angle EDF. Think about why. These two red angles I'm coloring in, why are they congruent? Hopefully you're noticing supplementary angles, and we know that angles supplementary to congruent angles are congruent. So now we've got sides congruent, angles congruent, and with our next piece of information, our given that angle AGB is congruent to angle EFD, which I'm going to mark. Let's mark that in a different color. How about green? So these two angles are congruent by given, and we can see our second set of triangles are now congruent. Triangle ABG is congruent to triangle EDF, and that reason would be angle side angle. And now we can show that AG is congruent to FE line segments by CPCTC. And actually there's another way we could have proven this, and that other way actually involves steps 1 through 3 would be the same, but then we'd use CPCTC a little bit differently, and we could actually have shown this blue triangle ACG is congruent to this triangle ECF. So if you have a minute or two, go ahead and examine that and see if you can figure out how we could have done the proof that way. One thing you'll notice about detour proofs, lots of times we can do them more than one way. So the way I do it wouldn't necessarily be the way you do it. Okay, now that we have done a problem together, I'd like you to do a practice problem on your own. Again, this is a pretty difficult problem, so if you're unable to do the problem on your own, I'll give you some hints in the next slide. But I'd really like for you to do this on your own. So I'd like you to get a piece of paper and something to write with, and then redraw the diagram. And I've given you a major hint here. I've already redrawn the overlapping triangles FAC and triangle HDB. I would highly recommend you do the same, or else I'm guessing you're going to have some major problems with this proof. So go ahead, write down the given information, what we're trying to prove, and see if you can work this one out on your own. After you've spent time working this on your own, go to the next slide and I'll give you some hints. Here are the hints I'm going to give you. First off, notice that the first given piece of information is that BG is congruent to CG line segments, which I'm drawing in red. Now, what that does is that gives us an isosceles triangle. Think about what we know. If the legs of a triangle are congruent, then the base angles are as well. Okay, so that would tell us that angles 5 and 6 are congruent. The second piece of information that we have tells us that AB is congruent to CD. Now, notice, AB is only part of the red triangle that I have drawn below. However, if we use addition, we know that line segment AC is congruent to BD. In the same way, if I examine the next given piece of information, FG congruent to HG, I am also going to see by addition FC is congruent to HB. So oddly enough, we've used addition twice in the same proof. Now that's a pretty hefty hint that I've given you. In all honesty, you should be able to prove those triangles congruent. Use CPCTC, the last couple pieces of given information, to prove triangles congruent again, and use CPCTC again. The second part of section 4.1 involves the midpoint formula. Initially, when you look at the midpoint formula above in red, it looks confusing. But to make a long story short, what we have is two coordinates, ordered pairs. We have x sub 1, comma, y sub 1, which could be any ordered pair. Maybe that's 5, comma 2, negative 8, comma 6, whatever it may be. And then we have x sub 2, comma, y sub 2. Now, we use the subscripts 1 and 2 for a specific reason. It helps clarify. So when I say x sub 1, y sub 1, really what I'm saying is the first x coordinate, comma, the first y coordinate. And when I say x sub 2, comma, y sub 2, I'm talking about the second x coordinate and the second y coordinate. X sub 1, x sub 2, y sub 1, y sub 2, they're just variables. But they're clarifying variables because we know in an ordered pair we always have x, comma, y. So the midpoint theorem tells us, and what I'm circling in red, to find the midpoint, the middle of a line segment, we're going to take the two x values, add them together and divide by 2, comma, the two y values, add them together and divide by 2. And the main way I like to look at this is what I have written in bold. You are finding the average of the x values and average of the y values. That's all it is. So we're going to take a look at an example on the next slide. So for the example on this page, take a quick look at what we're being asked. We want to find the coordinates of M, which is the midpoint of line segment AB. Notice A has a coordinate of negative 2, comma 5. B has a coordinate of 8, comma negative 7. A lot of times what I do first and foremost is to remind myself and to never make any mistakes, I'll call the first coordinate x1, comma y1, and I'll call the second coordinate x2, comma y2. Now, you don't have to do this, but if you get a little bit confused, and especially when you're looking at other things such as slope, sometimes this will help you. So our formula says we're going to take the x values, which are negative 2 and 8, add them together and divide by 2, and then we're going to take the y coordinates, 5 and 7, add them and divide by 2. And what you'll notice, when you add negative 2 and 8, you get 6. 6 divided by 2 is 3, comma, and then 5 plus 7 is 12. 12 divided by 2 is 6. And so our coordinate M is at 3, comma 6. And if we examine that line segment, AB, which I'm kind of outlining here in red, it makes a whole lot of sense. And it's very logical that that point M would lie at the point 3, comma 6. The next slide, I'm going to have you do a problem on your own. For this practice problem, I want you to find the three midpoints M, N, and K. So grab a sheet of paper, copy down the problem, copy down your coordinates, and then I want you to show your work and how you found the three midpoints. I've given you a hint. Basically, I've given you an answer. Double check to make sure you get negative 1, comma negative 6 for point K. If you did not, more than likely you had to have done something wrong. That is the 4.1 lesson. Hopefully you found this to be helpful. And we will be doing the first 30 minutes of class on Friday will be dedicated to start your homework. So I didn't give you an assignment for this section, and I did that on purpose. We're going to do it in class on Friday. Thanks.